current that was going in the wire that finally burst into flames came from another circuit. It actually had multiple chafe points going on. So what happened is it developed a short by one wire, one fairly heavy wire, chafing into a small wire, which then had another short. And so it ended up getting really, really hot, and its circuit protection wasn't designed for it. So, but its circuit protection was no longer in play because it had a short in two different locations.
Different circuits, right?
It was actually ended up being three different circuits got conjoined. That started the fire, and once the fire started going,
how would you solve that? Create more paths, like ground it individually?
It's not supposed to happen in the first place.
Well, I think better securing of the wires so they don't chafe the short. Yeah.
I think it started the insulation up above on fire, didn't it?
It started the insulation, but more importantly, it started taking out multiple systems. They actually, I think it was Halifax is where they were headed, where they were trying to abort to. And it was only about an 11-minute shot from when they first decided we're having problems.
Dump fuel in the ocean or something like that and hit the water.
But the system started degenerating to the point that I think they lost control of the airplane. Whether it was situational awareness lost control or enough systems got broken down that the plane wasn't flyable. But
was that night when that happened?
It was also at night, really bad, heavy weather, and they had descended very rapidly to get into Halifax, and they almost made it to the coast. It was very, very close to the coast. So yeah, sometimes all the best laid plans of monkeys and mice doesn't pay out. I think we had another one. I don't remember what actually started it, but a fire in the aft portion of the airplane, electrical fire started. They were, somewhere in the Midwest at 42,000 feet, something like that. And the pilot put it on the ground in less than 5 minutes.
Man.
Yeah, it was pretty amazing. On a small runway for the airplane. Well, what he did is he threw the gear out.
To slow down.
It's like fire realized, oh crap, threw the gear out at full speed. Tore all the doors off, tore everything off, but that really slowed the plane down. I mean, very quickly. He then threw all the spoilers and flaps out, pointed the nose straight down on it. Kept it at V&E until he got close to the ground and landed it on the first available runway. And by then the cabin was starting to get a fair amount of smoke in it. He did an amazing, or they did, was it he or she? Okay, so we can protect for high current. For example, the voltage regulator, the current limiting device on the voltage regulator. Isn't that a current protection device? Yeah. So we can protect on the input side, whatever inputs are on any of the power or grounds, or we could protect on the output side as well. And in fact, the battery surge protector things you use for your computers?
Yeah.
That's what that's doing. And in fact, they even have them where if you have your internet connection, it goes through there. So if anything gets hit with a lightning bolt or any other surge, it protects both inputs, outputs, as well as power and ground sources. All right. So it's also important that whatever your power supply is, does need to be appropriately rated. For the average little airplane, you don't want a 2 amp hour battery. You're going to need at least 15 amps or more. Same is true with the generator. So as we talked about this in earlier things, you really do, even though we could take and put a load meter in there and take all the load devices up to 100% of generator output, is that really the smartest thing to do? I mean, you could do it. The rules let you say you can do it. It would be a major alteration of the airplane. I'm thinking most FAA inspectors would argue. But I would think if you're going to go through all of that, put a bigger generator on there. Okay, get an SGC, to 40 amp, get an SDC to put the 60 amp unit on there. Okay, make sure that total system loads are leaving you a little bit of leeway, a little bit of flexibility.
Quick question. You mentioned earlier that, you know, when you're securing the avionics master to start engines, is that because there's a high load coming onto that bus with
the
engine?
engagement of the starter.
Is the starter just drawing so much energy that you're worried?
So what is the starter as a motor?
What is a starter as a motor?
Is it a capacitance or an inductance?
Inductance.
It's a big inductor.
Yeah.
What happens when you turn inductors off?
It still has
It has
residue.
sure.
All that magnetism likes to go somewhere.
That's
doesn't
to go somewhere, yeah, that residue.
So you now got 300 amps going through that starter and you shut it off.
It's got to go somewhere.
It's going to try and go somewhere, and it would be very happy to go through your $40,000 worth of avionics.
Okay.
Would love to.
Love to.
Yeah, of course. It's gonna. Okay, let's see. We're going shopping. What's the most expensive thing?
Okay.
That one. Yeah. Why not, right? Now the guy that makes the most expensive thing, last thing in the world he wants is people thinking his thing is a piece of crap, right?
Right.
So they're going to do everything in their power to make the input power supplies have good buffers and good circuit protection. But nonetheless, now the other side of it is, why leave the battery draining on with all these avionics on when you're hitting it with 300 amps?
Yeah.
Shut it off. You're going to fiddle around and putz around with stuff anyways.
Right.
Then you get ready to start it. The batteries probably come back up a little bit to a surface charge. We'll do a better job of starting anyways.
Okay.
Okay, so if we take an amp meter and put it between the bus and the battery, it will read minus, meaning that the current or that the voltage of the battery is less than the voltage on the bus. Therefore, the bus is charging the battery. It will read plus in the case that the battery is discharging. I said that wrong. I said that backwards. When the battery is charging, it reads plus. When the battery is discharging, it reads minus. Minus is bad. If the battery is discharging, there's really only one time the battery should discharge, right? When you've got the starter on.
When you're using it.
No, not when you're using it, but when you got the starter on.
Okay.
At all other times, the battery shouldn't be discharging. Everything should be running off the generator.
Right.
It'll get recharged. The only time the battery really becomes the main power supply is when the Jenny stops jennying. Now you've got 12 minutes or 45 minutes or whatever that time is for the battery to do its thing. Now that said, I gotta tell you, I spent a lot of time operating equipment. Big diesel engines, little bitty engines, airplanes, boats, cars, trains. Well, not so much trains, but a few buses. The amp meter is not necessarily the best indicator for what's going on. It's useful, but a voltmeter is far more useful. Being able to know what the bus voltage is tells me a whole lot more, because I know what the battery can do, its maximum output. I know what the generator can do. I know what all these different components can do. Now, if you look at the regs say you got to have the amp meter, right? 91 says you got to have something in there. I would rather have both. They also say that if you have an amp meter, meaning it's between the bus and the battery, although it's not part of the starter circuit. That's the other thing to make sure. So battery goes like this, big fat lead. It goes out like this, master solenoid, big fat lead, starter solenoid, off to starter, right? Also coming off of here, smaller lead to the amp meter shunt, and then off to the bus. That way, all the current that's going through the starter isn't going through our shunt. Shunt isn't designed to handle that. If the generator Ginny starts to recharge things, it'll do it back through this, back to there. Okay. Now the reason they say 80%, if I do it like this, and I'll draw the meter movement in here. Take a little meter right here, it goes into the meter, and then there's a little amp meter, that's minus and that's plus. Okay. That guy is just a Darcy ball movement measuring the voltage drop across that shunt. The reason I pick 80% is I need to allow 80% for all the users and 20% to recharge the battery. If, on the other hand, I go out here to my generator and come in here and put my shunt here with my little meter. Now what I'm going to do is just have the meter go from 0 up, because current can only go one way here. This is actually, instead of being called an amp meter, they call it a load meter. It's sort of weird. So if I use a load meter, I can now put, if I've got a 50 amp alternator, I can have 50 amps of users. I think the logic here is a little stupid. I can have 50 amps of users. So that means I can fire the engine up, get the thing started, right? Now my battery is 35% depleted.
Love the sound effects.
I'm in a hurry, I turn everything on. Okay, I turn everything on. So now I just turned all 50 amps of stuff on, plus I still got to charge the battery. And my load meter's going pegged over there. Well, nothing in the reg says I can't do that, even though I'm way overloading the generator. That's why, to me, it's nuts to ever have a generator have the loads being close to the same amount that the generator can put out. It's just absolutely crazy. Now, I think having this and that and a voltmeter is probably pretty useful to you. However, having now thrown that out there, the stupid little voltmeters that you buy to put in an airplane, they're not that precise as instruments go, as opposed to your Simpson meter or your DVOM, which is going to give you far more accurate information. They do now have some nice digital displays that are pretty accurate. Electronic management systems that give you reasonably accurate data, but okay. Well, let's talk about some of the loads. They kind of fall into a couple of groups. The first one are going to be your electrical mechanical stuff, things that make motion. They put the gear up, they put the gear down, they drive the hydraulic pump, they move the flaps, they start the engine. What else? They make they turn the little fan on to cool the avionics or to cool the pilot. The next group is going to be things that make light. This used to be fairly substantial. It's not so much anymore because we've gotten better with LEDs. Then the last group is going to be all others, which is primarily going to be data devices. Your radio, your navigation, your GPS, computing systems, engine meters, okay? Engine meters or other airframe sensors. Fuel level gauges, that type of thing. All right. So while they are turned on, motors typically use the most power per unit of time. However, most of the time motors don't stay on very long, right? I mean, starter. 5-10 seconds for every flight. Landing gear, one's up, one down. Unless you're really screwed up. Flaps a few times, all for limited duty. The one exception is going to be things like a fan, which a cooling fan will be on, may stay on continuously. The other one would be like a drive servo, maybe something driving a trim tab, driving an autopilot. Those guys are going to be back and forth. So you could say they're pretty much continuous duty. Now it's also, one should note that sometimes things like fans, you won't see them too often in some types of airplanes, like a turbine-driven airplane, because you've got customer air coming off of the turbine compressor. You already got, a 10 million horsepower fan. What do you need a little bitty electric one for? That said, our world is changing. Boeing is doing it as we speak. We're getting rid of bypass customer air. And, yeah, so the drive servo is pretty common. These guys, interesting. The world of technology around drive servos has gotten very, very, very different. Not only are they a lot cheaper and a lot more reliable, they produce a heck of a lot more power, physical force, and they're a lot more efficient in terms of current use and reduction in heat production. So we have done a lot of good development in the world of drive servos. So motors are always inductors. When inductors turn on and when they turn off, they create a spike. So you must account for that. And if you have AC going on or pulse DC, you may need to account for inductive reactance. Now, what's interesting about drive servos is almost always drive servos will come with some type of a controller. Okay, so the controller device here, servo motor driver, what they call it here. This will receive instruction codes from whatever the master computer is. Those instruction codes then get translated into digital on-off pulses that tell this motor to turn not at a specific RPM, but a specific number of units of rotation in a given period of time. So it's more than just, it's like, it's going to go, 20,000 units of operation in 1 second. Well, if there's 8 units per revolution, then it's going to go really, really fast, right? Or it may do it really, really slow, depending on what its instruction is. So these guys end up being very, very, very precise. They also, and when we come back into it, when we talk about motors, you'll see there's really 2 types. One that doesn't really know where it's at, but it has given specific motions. The other one also has a sensor in there that tells the computer where it's specifically at. Okay. So for example, in most of your printers, the printer has no idea where the motor is at. The servo comes on, and the printer goes to the stop. That tells it where it's at. From there, it now knows I've got a total of 9,000 steps this way. And I'm just going to keep counting, so I will know where it's at all times. And with each new print, I'm going to run over there and just recheck my stop. Okay, so that's a bit of programming that has to occur, but it's a much less expensive motor. So a lot of this stuff you don't get to fix in the field. All you can do is replace. Certainly, if you see evidence of El Melto, worn down beyond way worn down, lots of arcing and sparking, then at the very least you can say maybe this thing hasn't been maintained well, or maybe something else is wrong. Let's dig deeper. The other thing about a motor that can be a little unusual is when we have a tendency, this is the bottom of the servo, and the driver, the transistor driver for turning the servo on got fried. one of the things I would question here is, it may be that there's not an electrical problem elsewhere. It may be that the drive servo itself is binding. There's something not letting it go, so it's overloading. So maybe a mechanical problem. So lights and heaters, this is kind of a fun one. I pulled out a diagram of a cruise ship. Okay, a lot of your cruise ships have gone over to electrical production. There's 4 2140 kilovolt amp diesel generators or turbine generators. These are probably diesels. They're located throughout the ship. They drive some things, like they drive the stern motor at 600 kilowatts. One of the main azipod or azimuth motors at 3100s. There's another one. Actually, no, these are the 2 main drive motors that drive the ship through the water. So all of these are bow thrusters and steering devices, right? Main thrusters here. And then over here, you look at all the lighting. 600, 200. Actually, no, that's 800 and 200. So 1,000 and 1,000. So literally, one of these engines is used to drive all the light bulbs and toasters on the ship. I don't know if you've ever been on a cruise ship, but do they ever turn the light bulbs off?
I don't think so.
No, man, 24/7, lights are always on. It's party time. You're on a cruise ship, man. They're always cooking toast and making pizzas and doing whatever they do on a cruise ship. I don't know, I was on one once. It was the most boring experience I've ever had. However, well, I've spent a lot of time at sea and working. And when you're on a boat, a working boat, you work. There's always something on a ship that needs to be doing. So just sitting there going, give me something to do, please. And playing Yahtzee isn't high on my list. Anyways, lots and lots of power going to lights. Guess what? That's going out the window because of the LEDs. Okay, the truckers are the ones that are really taking it on, as well as local municipalities. All of those stoplights now, you guys are seeing them more and more and more, stoplights being converted to LEDs. So we're starting to reduce significantly. Here, we're doing a better job in terms of the motors, making them more efficient. But there's only so much you can do. A motor is already pretty efficient compared to a combustion engine. So there's only so much you can do in that department, because you got this 1,000-foot long ship that weighs 900 tons and you're shoving it through the water, right? Or airplane or whatever. All right, heaters are that's sort of the one realm that's a little bit different on airplanes than anyone else. In the world of airplanes, we really don't use heaters other than maybe the coffee pot. I suppose you could call a microwave a heater, but typically, if it's a bigger airplane, we have plenty of hot customer air. That compressor makes the air quite hot. So we can definitely heat things up, heat the cabin up, do whatever you want. In a little bitty airplane, we'll just take and wrap a little shield around the exhaust pipe and duct some hot air from there into the cockpit, keep it warm. It's sort of the medium-sized airplane, like either a little bizjet or a medium-sized twin, Queen Air, Duke, or something like that, where it's a little hard. You got the engines way out on the wings. It's a little hard to get the air in from there and have it still be warm enough to be useful. So in that case, what we do is we just make a combustion heater. And I'm not going to get too deep up into this because we deal with this in cabin atmosphere. But these guys, we don't actually use electricity to make the heat. We use fuel source, whatever the primary fuel source is on the airplane. The only electrical power is to run a couple of little blower fans in the unit. So we actually don't use electric heaters that much in airplanes. So that top sentence used to be true. I'm gonna say it's probably not true anymore. While we do still have incandescent lights in many places, I'm pretty sure that we can say, with the advent of LEDs and the little coil type neon lights, or specially shaped neon lights, that for the most part, certainly incandescent lights are not the most often the most often used light anymore. So the incandescent or the neon light, commonly called neon light, what it really is an ion beam being sort of generically transmitted between some very high voltage 700 volts electrodes. You get this really weird ion gas lighting moving back and forth. That's what's happening in these right now. It's ugly. It's not very light. It doesn't have a lot of light, and it really looks weird. However, to make it work better, what they do is they coat the inside of the glass with a substance called phosphorus. And when the weird, funky photons hit that phosphorus, they excite it, and they emit a very nice, even, uniform glow, which is why these look really, really nice. If you got the phosphorus powder coating out of the inside, these things would be terrible, and you wouldn't see much light coming from them. Okay. So it's important to note that with these devices, they have a tendency, and for primarily lights and motors, they have a tendency to have what's called an inrush current. When I first, and we haven't talked about motors yet, but when I first turn on a motor, the inductor is going to have a whole bunch of current running through it. It's going to take a while to build up, but the motor is going to start spinning. And once it starts spinning, it starts creating that counter reaction that we talked about, that the generator has. And that counter reaction, depending on the load on the motor, is going to start opposing the current flow. So the current use is going to go drop way, way down. Same thing is true with an incandescent light bulb. What happens when you turn it on? Isn't it a dead short? Current's going to go whaling through that little wire. But what happens when the wire gets hot?
Becomes more resistant.
Its resistance goes way up. So the current, while it gets brighter and hotter, current's actually going down. So when you first turn it on, it might be a 5 amp bulb, but when you first turn it on, it might be, at 10, 12, 15 amp for that initial, and then it'll drop back down. That's why light bulbs always fail when you first turn them on. Okay, you guys have all had that happen to you. Click, boom, goes real bright and blows out. That's because it finally got, the metal had gotten fatigued enough that inrush current caused it to be a fuse instead of a light bulb. Question.
They do that on purpose. Anyway.
Well, nothing should last forever.
So if I took the switch and did this, I'd be using a lot more current than I would if I just turned it on once, left it on all night.
Yes.
So it's better to leave it on.
Yeah, probably.
So
Or just turn it off.
there's a political element here
Yeah.
between you and your significant other.
Yes.
If you're going like this, you're using more current. On the other hand, if you turn it on, you're there for 5 or 10 minutes, turn it off when you leave the room. Come back in 10 minutes, turn it back on. You're using quite a bit less current. You are causing the bulb to wear out quicker, though.
Oh, okay.
Turbine engines are another one. You got a finite number of times you can start it up and shut it down. The same thing is true with light bulbs. But where's the amount? Certainly, if I turn it on and left it on for 2,500 hours, that's how long it would last. That's how they test them. But if I turned it off and on and off and on and off and on, I wouldn't get 2,500 hours out.
You're shortening their lifespan.
Yeah.
Well, they didn't tell you how many times you can turn it on and off on the package.
Well, call it a day.
Damn.
Yeah. That's why you can buy for a lot more money a specialized GE 4507 or 4505 light bulb with a turn-on circuit that dampens the inrush current. So then it will last much, much longer.
Yeah, how much is that gonna cost?
Probably 8 light bulbs, so, you know, yeah, they're kind of expensive. But,
Are they worth it?
well, you gotta say, what's the cost of 8 light bulbs? Right?
What was the number on that one?
Versus this, huh?
What's the number on that light bulb again?
I think it's 4507.
All right, we use those a lot on the air.
Landing gear light, standard landing gear light. Standard GE, it's kind of like about that big.
Right.
I
I think it's
suppose,
4505 or 4507, something like that.
suppose it's how many times you want to go up and down the ladder too, right?
Mhm.
So the real issue is that cost me 8 bulbs, but if I buy 8 bulbs, they'll last longer than that thing cost. However, you also include the cost of installing them. And if the landing light is out, is the airplane grounded? Et cetera, et cetera. So maybe it is worth buying the more expensive.
Yeah.
Or go high dollar and buy the LED version. That's only $800.
Oh, that's it.
You know how many screws it takes to change a light bulb on a typical Beechcraft? 27 screws.
Boy, if you.
That's a lot of work.
So here's an example of a chart for inrush current and your derating factor. I'm not sure derating is quite correct, but so in a 24 volt system with a lamp, if the lamp uses 1 amp of current, I want the switch to be able to handle at least 8 amps and the rest of the circuit to be able to handle at least 8 amps. Okay? Because that's when it's going to get when you turn it on. So inductive devices, a little bit higher, resistive, motors, okay, and then the 12 volts, everything's stepped down a little bit. All right, let's stop here. My voice.